asked this question about 2 years ago, and like only 2 hands raised. Because, and even among my peers, my faculty members, there's a lot of faculty members who don't want to teach distance. They have their reasons. Okay.
Quick question, how would tests and things like that work? Would they be live from the campus tests, or would they be online days?
You know, for graduate students, a lot of these guys, I mean, I got a guy in Brazil, I got a guy in California, they're all over the place. So I don't, for my graduate classes, I don't do exams anymore. It's different for graduate students. It's different. For undergraduate, I don't know. And if it's only offered to this community, you know, the Auburn community, not offered to anybody else, I might say, yeah, we still have exams, but they will be in, you know, we'll meet here as for our lectures, but then because there's another section of distance students, maybe periodically we had to meet in the auditorium and we would take our exams in the auditorium, just have a big enough. That's a possibility. I did have some online exams in Canvas for a few semesters for this course, and it didn't work out very well. Everybody made 100. I don't know why. I don't know why. You know, I went through all these processes of, like, you know, scrambling the problems, scrambling the answers, and people said, oh, I mean, people who are in the education department, they say, oh, it's obvious why they're all making 100s, because while one person's doing the exam, his buddy is working out the problem for him, and they're working on it together. I said, they can't be. I'll say, oh yeah, they can. And so obviously, I'm still learning. So the answer to the question is, I don't know the answer to that, and I would have to work it out. There was some things about the online exam that I liked, and I think the students liked. There was the system did the grading for me. I didn't do any grading. All I did is I just checked the system for all the problems that were marked wrong by the computer, and then I would say, I would regrade it. But I wasn't looking at all the problems. I was only looking at the ones that the system marked wrong. And then, for example, maybe the answer was 0. But instead of typing in 0, the student actually accidentally typed O. The computer says wrong. Well, I go through manually, I say, oh, that's an obvious. He meant 0, it's obvious. O and 0 are kind of close on the keypad, and just hit an O. So I would regrade it and correct it. Okay, so maybe I will offer 3,500 in the online form at some future time. Okay, so we're today going to look at sketching the root locus. We're good, Matt?
Yep.
Okay, thank you. So we looked at doing the root locus by computer. The computer does a pretty good job. We were going to sketch it by hand mainly because we just wanted to have a sanity check on what's going on. And so the material that we're going to look at is in chapter 7 of the book. I wanted to kind of point out there's a table. There's a table, table 7.2. So that's what you want to kind of take a look at. Now there's some things about here. I mean, I like this book for a lot of reasons, but there are some things that I probably would have said a little differently. It says here 7 steps. 7 steps for sketching a root locus. The reality is, yeah, you want to do everything by hand and get it accurate when you do all 7 things. But the reality is we will probably do 3.5 of them. Okay? To get a reasonable good sketch, you only need about half of the sketch rules. So I'm not going to go through all 7. And I probably would not use the word steps, because steps seem to be you do one thing, and then you do the next thing, and the next thing, and then you get the result. The reality is you don't have to do it in a particular order. There are 7 rules that have to be obeyed, but you don't have to do them in this particular order. So I would probably change that to be the word 7 rules for sketching a root locus. Okay? The other thing that I encourage you to do is go look at the back of the book online, and there's another table at the back of the chapter, if I can find it here, that has a bunch of diagrams already sketched. I'm trying to find it. There was a table back here. Here. So it's at the end of the chapter, and so there's a bunch of these transfer functions. There'll be a bunch of different. There'll be a bunch of different examples, just generic shapes, and they say this is what it looks like, that's what that looks like. and you can kind of just go through and just get an idea. So for those of us who like seeing things on paper, because it's all together in one place, I encourage you to take a look at those things. But we're going to sketch the root locus today, and basically there's just a few rules to remember. Okay. And so let's go ahead and do that. You can take a look at table 7.1, but I'm just going to write some of these rules as we do some examples today. And so let's start off with just a few things. First of all, label your axes. Okay, label the axes. And the axes will be labeled real and imaginary. Because we're plotting poles. We're plotting poles. Poles are complex numbers in general, so they'll have a real and imaginary part. The second thing what we'll do is plot the poles and zeros, and the poles will use X marks, and the O's will use O marks. Plot the poles and zeros on the open loop function. And I should maybe refrain from using numbers. Let's just put stars up here. They don't have to be done in this particular order. You can label your axes at the end if you want. It helps to plot the poles and zeros of the open loop function to get started. And then what we can do is there's several rules that we want to do. What I would do is, one of the easiest things to do is to figure out where there may be loci, figure out where the loci are on the real axis. Figure out locations of the real axis loci. So let's go ahead and pause for a moment, and we'll just do an example, just doing these three rules. Okay? So this is a system, S plus 2, like this. Oh, let me put another one up here. Let's go S plus 3. S plus 3. So we'll start off, we'll draw our axes, label them real and imaginary. And then what I typically do is I plot the poles and zeros. So this is a 0 at S equal to -3, poles at S equal to 0 and -2. So I would go pole, pole, 0, like this. Now, the rule says figure out locations of real axis loci. So that means we need to draw a line. We're going to draw the locus. And so the question is, do any of the loci lie on the real axis? Okay, and that's one of the easy rules to take care of first. Okay, so this is what I do. There's a kind of a mathematical way of discussing it in table 7.3, but I'm not going to use mathematical terms. What I do is, you see that the real axis is divided into sections. It is subdivided by X's and O's. Okay. What I mean is, when I look at this real axis, I say, there are subsections. There's this section to this side of the X mark. There's this distance between here and here. There's a distance between here and here, and there's a distance from here back to -infinity. The real axis has been chopped up by X's and O's. So figure out locations of the real axis loci. The real axis is subdivided by X's and O's. Okay? Stand in a section, subsection. Think of it as a line segment. Just stand in a segment. And look to the right. Stand in the section and look to the right. And the question is, odd number of X and O's Here I said, we're trying to figure out if on the real axis there are any lines that need to be colored in, any loci, any possible closed loop roots where they lie on the real axis. I look at the real axis, I say it's been chopped up by some X's and O's. Okay? If there are X's and O's out here, I ignore them. They have no bearing because they're not on the real axis. So what I do now is I stand in any subsection. Just pick one. Now we've got to evaluate the whole line, but for now, let's just pick one. So let's just stand right here. Look to the right. You look to the right and you count how many X's and O's you see and ask yourself if it's an odd number. You stand here, look over there, and I see 1, 2. That's an even number. So the answer is no. So don't color this in. Stand right here. Look to the right. I see 1. That's an odd number. Anywhere I stand right here, I look over there and I see an odd number. So this needs to be colored in. There could be closed loop holes on this axis, right there. So I would do this. Okay. And I would do the same thing here. Let me bring the words back on the screen. Figure out the locations of the real axis loci. Real axis is subdivided into subsections by X's and O's. Stand in a segment and look to the right. Is there an odd number of X's and O's? Yes, color it in. So that's the rule. The number of loci, I call them branches, is equal to the number of poles. So this system here has 2 poles. There's 2 poles. Okay. Because there's 2 poles, that means there's 2 loci. Number of loci is the number of poles. Loci start at poles and end on zeros, or go off the page. Go is spelled without an E. But me and Dan Quayle are friends. He spelled potato with an E, and I spell go with an E. Okay? They go off the page. So what that means is the number of loci is equal to the number of poles. They start at the poles and end in the zeros, or they go off the page. So I have 2 branches. So one of them has to start here and be moving this way. I draw a little arrow say that as K increases, one of the closest poles starts here and goes this way. As K increases, one of the poles starts here and goes this way. Okay. As K further increases, something is going to end up here, and something is going to go off the page. Okay. Now I've got to figure out where it goes off the page. Okay, so let's talk a little bit about how things go off the page. There's a thing called an asymptote. Asymptotes, these are kind of like guidelines. These are asymptotes for loci going off the page. Can't spell this one. 2 F's. For loci going off the page. Now, off the page in the book, it's going to be called going to zeros at infinity. That's a mathematical term that I don't want to explain. You know, we had this phrase here. It says that loci start at the poles and then end on the zeros. And then I said or, they go off the page. But another way to say it is loci start at the poles, x's, and then end on zeros, or they go to zeros that are off the page. So the thing that will be uniform or in common with both statements is that loci end on zeros. They may be finite zeros, the ones that you can see, they have O's, or they may be zeros at infinity. Infinity is off the page. But that's getting to be so mathematically speaking, and I try to avoid that. So asymptotes, these are guidelines for going off the page. So we got to figure out which way is the loci going to go off the page, and we need to put in some dashed lines and figure out how are the loci going to go off the page. Okay, so let me. This rule is probably the only complicated rule for sketching the root locus, and it's going to be divided into two parts. First of all, we need to determine number of lines, number of asymptotes, and their location. Okay. And then the other thing we can do is determine their angle or their shape. What is the shape of the lines? Okay. Number of lines and location and angle. Let me not put an A, let's just say. Okay. So number of lines is equal to the relative degree. The relative degree is equal to the number of poles minus the number of zeros. That's R. So in our example here, we have 2 poles, 1 0. Relative degree is equal to 1. So there will be only one asymptote. All right, now we need to figure out, where, what is the angle or the shape or the picture. And so there's an equation for doing it in the table, but I'm just going to draw the picture and then we'll back out the equation. All right, so let me make a table here. Here's R, and then here's the shape of the asymptotes. Okay. If you have only one asymptote, R equal to 1, then the shape looks like this. It's a dashed line going this way. Just make a dashed line, it's going this way. This angle, now think about here's the origin, real and imaginary. This angle is 180 degrees. So make it point this way. The second one is, and we saw this in some of our examples, if you have 2 lines, they will go like this. One goes this way and one goes this way. It'll be vertical like this. And if this is the real axis, this angle is 90 degrees. If we have 3 asymptotes, there's the real axis, you're going to have 3 lines. One will go this way, one will go this way, and one will go this way. And what do we think this angle will be? 60. Okay. Time for a quiz. 4 asymptotes. Will the asymptotes look like this? Or will it look like this? With 1 asymptote, 180. 2 asymptotes, 90. 3 asymptotes, 60. 4 asymptotes, 45. That's this one. Okay, so now you know this formula. 5 asymptotes, what do you think the shape will look like? What word would you describe to your mother? If I gotta draw 5 lines. A star, right? Try to make a star. Now the question is, which way is it oriented? Okay. the angle should be what? 1 is 180, 2 is 90, 3 is 60, 4 is 45, 5 must be 36 degrees, so 36 degrees. So you can get the formula in your head, okay? But for me, I just kind of remember what the shapes are. Let's go back to our example. Relative degrees equal to 1, so I just have one asymptote that goes off this way, so that means 1 must go this way. They start at X's and they terminate on O's and they go off the page. There's some other rules that we should draw. We need to complete this thing now. We're going to complete the diagram. And then, so we need to draw a picture where the locus is symmetrical. With respect to real axis. So with a little bit of experience, we would say, how am I going to get from here to two things starting here, moving like this as k increases. As k starts off with k equals 0, I start off here and here. As k increases, they go like this. And for a very large k, one of them goes here and one of them goes here. So I need to draw some picture which is symmetrical with respect to the real axis. In other words, if I fold it, the top part and the bottom part are on top of each other. They're mirror images. How can I draw something that does that? So one solution is this. So that would be a rough sketch. Then these are called real axis breaks. There's formulas for that, but I'm not going to hold you accountable for those formulae. Okay. 20 years ago, we did that, but now we don't. Okay, so. All right, let's do another example, and let's add some more details to our rules. So, label our axes real and imaginary. Draw our poles and zeros. There are no zeros. 3 poles. Okay. The 3 poles are here at the origin, one here at -1, and another one right here at -3. Let's say, because there's 3 poles, no zeros, that means the relative degree is equal to 3. So therefore, there are 3 asymptotes. And they will be shaped like this. But I need to put them somewhere here. Somewhere I need to figure out where they need to go. So I said earlier that asymptotes, we need to know the number of lines and their angle or their shape, but I didn't talk about their location. With the previous example, it didn't matter where you drew this line because the line was just going to be on the real axis pointing to the left. But here, I need to figure out where to draw these lines, whether I put it here or here or here or here. So there are some real axis asymptotes. We need to take a look at where they are located. And so the location of asymptotes we've got to draw this picture. We've got to sketch in these dashed lines on the picture. And where they're joined together, this point here, this is given a name. This is called the centroid. It's where all the lines come together. Centroid. C-E-N-T-R-O-I-D. Called sigma, centroid. How do I find that? What we do is we take the sum of the poles minus the sum of the zeros divided by the relative degree. Sum of the poles minus the sum of the, not the number of poles, not the number of zeros, but the sum of their actual values. And then divide by the relative degree. That's the location of the asymptotes. So let's come take a look at this picture here. Let's figure out where sigma is right here. A pole at 0, a pole at -1, a pole at -3. Subtract off the zeros. There are no zeros, so there's nothing. And then divide by the relative degree. The relative degree here is 3. Okay. So it's -4/3. -4/3 is about here. Okay. So I would sketch it, and my 60-degree lines there, 60-degree line there, and a 60-degree line there. Let's review some of the rules. Let's see. 3 branches, so that there must be one branch starting here, one branch starting here, one branch starting here. What rule have we not done yet? Oh, we haven't done the easy one, the real axis. Let's figure out where on the real axis there could be something to color in. So let's stand right here, look that way. That's an odd number, so I need to color all this in. I stand right here, I look that way, I see 2. Don't color it in. I stand here, I see 1, 2, 3, so it's odd. So there must be loci here and here. Loci start at the X's and they go to the O's, but I have no O's, so therefore they go to O's at infinity. They go off the page. So that means they must be going off the page this way, and this way. This way, this way, and this way. They start at the X's and they go off this way, so it probably does something like this. And that's the picture for that function. Let's do one of the something similar to one of the examples in class the other day. Let's do G3. Oh, I'm going to do something like this. I'm just dreaming one up here. So I have a 0 at -3, poles at -10, and this is complex, -1 plus or minus j1. Relative degree is equal to 3 poles, 1 0, equal to 2. So I have 2 asymptotes. I should draw asymptotes that look like this. And I need to figure out where on the real axis this is located. Sigma is equal to, let's add up everything. -10, -1, -1. Okay, let's add these all together. Minus a -3 divided by 2. Okay. This -10 comes from here. This -1 comes from here. This -1 comes from here. What have I conveniently thrown away? I threw away the complex components. Why do I throw away the complex component? Why is it okay to throw away the complex components?
It's not on the real axis.
Because it's not on the real axis. True, that's not on the real axis. Let's suppose I don't throw away the complex parts. Let me add it together. What do I get here?
It's canceled.
They cancel. Okay, the complex parts cancel. And so because I don't want to clutter my page, I just threw away the complex parts. So some books will actually say their formula will be not just the sum of the poles minus the sum of the zeros. They say sum of the real parts of the poles minus the sum of the real parts of the zero. And it's because the imaginary parts are not on the real axis. We're trying to calculate something on the real axis. And the things off the real axis are going to cancel anyway. So imaginary parts cancel. So do the shorthand and just run it through this way. Okay, negative 10 minus 1 minus 2, that's negative 12. Minus a minus 3, which is plus 3. Negative 12 plus 3 is negative 9. Divided by 2 is negative 4.5. Okay, so that's enough for us to sketch our root locus kind of quickly. So let's do this. Real and imaginary. Plot these zeros in poles. Got a pole out here at minus 10. 0 and minus 3, which are roughly a third of the way across, so that'll be right here. 0 at minus 3, pole at minus 10. Complex poles at negative 1 plus or minus j1, they're going to look like this. Asymptotes, 2 of them, located at negative 4/5. Not 4/5, 4.5. Negative 4.5. Negative 4.5 is roughly here. One asymptote going this way and one going this way. Negative 4.5. So, okay. Let's do the real axis. Loci, they're easy to do. I study the real axis. I stand in any section. I look to the right. I say 1, 2. That's an even number. Don't color this in. Stand anywhere in here. I look to the right. I see 1. Color this in. I stand anywhere here. I look to the right. I see nothing. That's an even number. Don't color it in. So this is what I need to color in. Loci start at the poles, loci start at the x's, and they end on the o's. So as k is increasing, the closed loop poles one of the closed loop poles must be evolving its values somewhere along this region. X's start at the x's and end on the o's. The number of branches is equal to the number of poles. So I've got one branch kind of drawn in. I need to draw 2 other branches. And they need to go to o's, but this one's already occupied, so this must be doing something maybe like this. It's close enough. Now you may ask, is it possible for the lines to go across and then come back around? Yes. This is not a do not cross line. It's a line that says, as you get far away, as you're sitting way in the back of the room there, where are some of the branches going? One's going this way, and one's going this way. The details right around here in the middle could vary. This is one picture that is not unreasonable, given the few rules that we're going to apply. But let me draw another picture which could also be true. Minus 10, minus 3, minus 4.5, real axis. Okay. Let me draw a really crazy one. Maybe it does something like this. I draw it symmetrically. As K increases, it does this. As K increases, they do this. They hit the real axis. And then one goes this way. And then one goes this way. Okay, there's two branches here. Starting at the axis, as K increases, they go like this. They hit here, and then one continues this way, and one continues out here. Meanwhile, this guy's coming in like this. They meet right here. And then they do this. Which one's correct? Both of these pictures satisfy all the rules. And on an exam in this class, I would accept it. How do we find out for sure which one's correct? These days we use a computer. I grew up in Tennessee in an era when Tennessee football was not really good. And I thought it wasn't very good. Now Tennessee football is like a dumpster fire. Yeah. So when I came to Auburn, I went to my first game and I sat in the stands. I said, man, this feels like a high school game. You know, small stand, everybody's friendly. You know, Tennessee, when I grew up, it was kind of vicious. So I've raised my family here. All three of my kids went to Auburn. I don't donate to Tennessee anymore. I donate to Auburn. So I love Auburn. I wish the boys do well in everything they do. But sometimes the blogs say, you know, Gus needs some help on his offensive creativity. So this running back going this way and that way, the tight ends going this way, and we're going to plaster that linebacker over there. All right, so the answer is, you know, really to do real work, professional work, you're not going to do this anymore, okay? This is just a sanity check. Both of these pictures satisfy all the rules. If we wanted some details, we would have to go and test. We would pick a point and say, is this point on the root locus? Or maybe we'll come over here and say, this is much different than that. I should ask myself, is there a point? Is this point on the root locus? Could this point be on the root locus? I might test a few points, just randomly out in the world and say, could this be on the root locus? And we will do that next week. And so let me just close and just say, both these pictures, both these diagrams satisfy the basic rules that we've covered. They don't cover the more advanced, I'm not covering the more advanced rules because in reality, we just need to get a rough idea of what's going on. So for example, with either of these pictures, I will get the same consistent question, answer to this question. Let me ask this question. Will this control system be stable for all gains? Will the control system be stable for all gains? Yes, because all the loci lie in the left half plane. So no matter which picture I look at, I'm going to get a consistent answer. Okay. What will be the nature of the response when the gain is large? What will be the nature of the step response? It'll be bounded, so it's stable. Will it oscillate? Will it ring and then die out? Yes, right? Because we have loci that are complex. That means there are closed loop holes that could be complex. That means the response will ring. So the answer is consistent no matter which diagram I use. So for initial work, this is good enough. If we want to do more detailed work, we'll get on the computer. All right, let's stop there.